Hey everyone, and welcome. Today, we're going to dive into something we see every single day, but probably don't think much about: a simple beam of light. But as we're about to find out, that light is carrying a whole universe of secrets, and you and we're going to unlock them together.
Okay, so let's just jump right in. You know that sunlight streaming through your window? It looks pretty simple, right? Just white and bright. But is that the whole story? Oh, it's not even close. There's so much more going on.
So, this whole story really kicks off back in the 17th century with the one and only Sir Isaac Newton. Picture this. He's in a dark room, he lets in just a tiny beam of sunlight, and he passes it through a little glass prism. And what he saw on the other side? Wow. It changed science forever. He saw a beautiful, brilliant band of colors, just like a rainbow.
And this incredible effect, this beautiful splitting of light, well, it has a name. It's called dispersion. What's happening is that as the white light zips into the prism, all the different colors hiding inside it, they all bend at slightly different angles. And that's what fans them out into that amazing spectrum we can see. So, what Newton found was that this spectrum was made up of 7 main colors. We're talking violet with the shortest little waves, all the way to red with the longest. And you can probably remember the order from school with that classic acronym, VIBE-GOR. Each of those colors has its own specific wavelength, which we're measuring here in angstroms. And just to give you a sense of scale, an angstrom is so tiny that 10 billion of them fit into a single meter. Wild. Okay, but here's where things get really, really interesting. That beautiful rainbow, that VIBGEOR that our eyes can see, it turns out that's just a tiny, tiny fraction of the whole story.
Get a load of this. This right here is the complete electromagnetic spectrum. It's all the different kinds of light that exist in the universe. And you see that little colorful sliver right in the middle? Yeah, that's everything the human eye has ever seen. In all of history, the rest of this massive spectrum is completely invisible to us.
So beyond the red and violet that we know, there is this vast, invisible universe of light. Let's take a quick tour of this hidden rainbow, okay? And we'll start with the most powerful waves out there. First up, we've got gamma rays, with wavelengths smaller than a single atom. These were discovered by Henri Becquerel, and they are the absolute heavyweights of the spectrum. I mean, they're so powerful that when you focus them, doctors can use them in radiotherapy, kind of like a microscopic laser, to zap and destroy cancer cells. Next up, something you've definitely heard of: X-rays. Discovered by Wilhelm Röntgen, these guys have that wild ability to pass right through our skin and muscles, but get stopped by our bones. And that gives us the incredible superpower of being able to peek inside our own bodies to spot a fracture.
Just beyond the violet light our eyes can see, we find ultraviolet, or UV, rays. These were found by Johann Ritter. Now, you know these as the rays from the sun that can give you a pretty nasty sunburn. But here's the twist. A little bit of this very same radiation is what our bodies need to produce vitamin D. And we've also figured out how to use it to sterilize surgical tools. So it's got a good side and a bad side.
Now let's hop all the way to the other side of the rainbow. Just past the red light, we find infrared rays. And the way William Herschel discovered these is just great. He was measuring the temperature of the rainbow, and on a whim, he put his thermometer past the red light and noticed it still got warm. We feel this radiation every day as pure heat. And yeah, it's what lets us change the channel with our TV remote.
Keep going to even longer waves, and you get to microwaves. First demonstrated by Heinrich Hertz, these things are the real workhorses of our modern world. I mean, think about it. They carry our cell phone calls, they let us track airplanes with radar, and of course, they heat up last night's pizza. And finally, with wavelengths that can literally be as long as mountains are tall, we get to radio waves. Guglielmo Marconi really pioneered their use, and because they're so huge, they're perfect for traveling massive distances, carrying the music, news, and shows that fill our homes and cars.
So, from gamma rays all the way to radio waves, they're all just different flavors of light. They just have different wavelengths and different frequencies. But how exactly are those two things connected? Let's pop the hood for just a second and look at a quick calculation. The formula is actually really simple. A wave's frequency is just the speed of light, which is a constant, divided by its wavelength. So for our yellow light, we take that crazy fast speed, divide by its super tiny wavelength, and we get its frequency. And the number we get is just staggering. It's 5.4 times 10 to the 14th hertz. That means 540 trillion wave crests of yellow light are hitting your eye every single second.
That's absolutely mind-boggling.
So, we've got this entire invisible rainbow of light beaming down from the sun all the time. But how does that actually shape the world we see every day? Well, it finally gives us the answer to that age-old question we've all asked, hey, why is the sky blue?
The answer, the key, is a process called scattering. When sunlight hits all of the little molecules and dust particles up in our atmosphere, those particles basically grab the light for a split second and then shoot it back out in every random direction. You can kind of think of it like a trillion tiny disco balls floating in the air.
Now here's the cool part. Those tiny little air molecules are way, way better at scattering light that has a short wavelength. So if you think back to our rainbow, which colors have the shortest wavelengths? Right, blue and violet. So while the longer wave red and yellow light tends to just pass straight through the atmosphere, that blue light gets bounced around and scattered all over the place, coming at our eyes from every direction and, well, painting the entire sky blue.
All right, so you've officially taken the grand tour of the full electromagnetic spectrum and even seen how it explains why the sky is blue. You ready for a quick little pop quiz to see what stuck? Come on, let's find out.
First question for you. Think back to Newton and his prism. When that white light passes through and splits into a rainbow, which of these colors bends the least? Is it A, violet, B, yellow, or C, red?
And the answer is C, red. If you got that, awesome. Because red light has the longest wavelength in the visible spectrum, it gets deviated the least as it goes through the prism. It's violet, with its super short wavelength, that bends the most.
Okay, one more for you. Which of these invisible waves do we use for stuff like night vision goggles or thermal cameras? You know, to take pictures when there's no visible light around.
That's right, it's infrared. Any object that has heat, and that's pretty much everything, gives off infrared radiation. So night vision tech just picks up on that radiation, letting us see the heat signatures of things even when it's pitch black.
And really, that just gets you thinking, doesn't it? For almost all of human history, that tiny sliver of a rainbow was the entire universe to us. This whole invisible reality of X-rays and radio waves and everything else, it was here the whole time, completely unseen. It just makes you wonder, what else is hiding in plain sight right now? Just waiting for us to find a new way of looking at the world. Thanks for joining me on this journey today.